Okay, hey guys, it's Mrs. Myers, and today we're going to do lesson 12.2, chords and arcs. Again, we're still working in circles, and this is going to relate to central angles. A new vocabulary word we have here is chord, and a chord is a segment whose endpoints are on a circle. So a chord, we can draw a little diagram here, would be something like this. So segment AB is a chord of a circle. Okay, AB. Anything where the two segments are on, the two endpoints are on the circle. So this question is an interesting question. What is the largest chord that can fit in a circle? When you think of what it would be, the largest chord would go across the widest part of the circle. What would we call that chord? The diameter. It goes right through the center. The diameter is a type of chord. So if there's ever a time where they ask for chords from a given circle, a diameter could be listed as one of the chords. Okay, we have got a lot of theorems here. Let me just look ahead here. See all these theorems? I think there's 12 altogether. So that's a lot of theorems. Maybe there's 8, well, whatever. Most of them are the theorem and the converse, and they all relate to circles and the arcs, central angles, and chords. So most of it is pretty intuitive if you remember what we learned about central angles before and what we learned about arcs before. So this first one says within a circle or in congruent circles, we're going to talk about within one circle here. Congruent central angles have congruent arcs. In other words, if this angle is, let's say, 30 degrees, and this angle is also 30 degrees, well, since we learned that the arcs have the same degree measure as their central angle, that means that these two arcs are going to be the same. If the angles are the same, then the arcs are the same. Okay, so that's what this says. If the angles are the same, congruent, then the arcs are congruent. If then. The converse is also true. If you know the arcs are congruent, well, then you know those central angles attached to those arcs are going to also be congruent. Okay, so that's pretty basic. I think you guys can relate to that since we did all that work with arcs. The second set of theorems is also a theorem with its converse. It says within a circle or in congruent circles, congruent central angles, okay, so again we're talking about two central angles that are congruent, have congruent chords this time. So not the arc that's attached to or related to this central angle, but the chord. This chord is congruent to this chord. The chord is that segment that connects two endpoints on the circle. So it's the same two endpoints that also have arc AB. There's also a chord AB. So we're not talking about arc CD, we're talking about chord CD. So again, the theorem says if the central angles are congruent, then the chords are congruent, and vice versa. If the chords are congruent, then the central angles are congruent. Okay, so it just has to do with the concept that when you have a central angle, and as soon as you draw that central angle, you've involved a bunch of things. You've involved a chord that has those endpoints AB. You've involved chord here and an arc that has the same endpoints. So all of them are related. Okay. The next set of theorems says within a circle or in congruent circles, congruent chords have congruent arcs. So now we're not starting with the angles like we did before. These all had to do with, if we know the angles are congruent. Then here we're going to start with the actual chords, and we're going to relate it to the arcs. Okay, so these two concepts here, let's highlight this. Okay, this concept was with angles and arcs. Okay, angles congruent, then arcs are congruent. Here, and vice versa. Here, this is all with angles and chords. Right? If angles are congruent, then chords are congruent. If chords are congruent, then angles are congruent. Down here, this is going to have to do not with the central angles, but with just the chords and the arcs. If chords are congruent, then the arcs are congruent. If the arcs are congruent, then the chords are congruent. Okay? So if you're given a particular chord that has, let's say in this case, endpoints A and B, then the arc that has those same endpoints are also congruent. And vice versa. If you have the arc that has a congruent measure to the other arc in the circle, then the chords are going to be congruent as well. So this arc to this arc means this arc to this arc. So, sorry, this chord to this chord. So if the two chords in one particular circle are congruent, then their arcs related to them are also congruent, and vice versa. If the arcs are congruent in one particular circle, here to here, then the chords are also congruent. Okay, so they all have to do with each other. Seems like a lot of theorems, but they're all related. Okay, and this last one says, a little bit different, but this one says, within a circle or in congruent circles, chords that are equidistant from the center are congruent. So if we have two chords, A and CD, and we know that the distance from the center to this chord is the same as the distance from the center to this chord, so the same distance from the center, then the two chords have to actually be congruent to each other. If you think about considering a situation where here's a chord that's, let's say, 2 inches from the center, and then we make another chord that's not 2 inches from the center, let's make it 3 inches from the center. Well, what happens? The further away it is from the center, the shorter the chord is. You can see how it's much smaller. If we do a chord that is closer to the center, okay, so let's make one here that's only, actually let me go this way, only a ½ inch from the center. Well, now that chord is going to be longer because it's closer. The closer it gets to the center, the longer it is. The further away from it is from the center, remember we measure distance by the perpendicular distance. The further away it is from the center, the shorter the chord is. So it makes sense that if they're the same distance from the center, then they're actually going to be the same length chord. This is congruent to this. And vice versa, right? So the this should be marked as a segment. If OE is congruent to OF, so the distance is the same. I guess it could be equidistant. This should be an equal sign then. Instead of marking them congruent, if the two distances are equal, then the chords are congruent. And vice versa, converse. If the chords are congruent, then they are the same distance from the center of the circle. Okay, we'll practice a few of these, but I've got more theorems to teach you. This is a loaded section here. So if we look at this, which arcs are related to BC and DF? So the arcs that are related to segment BC and DF, so they're talking about here's this chord and here's this chord. The related arcs are just going to be BC arc and arc DF. That makes sense, right? Which central angles are related to them? Well, we've got the central angle here, so it's going to be angle BOC and angle DPF. oops, DPF. Okay. Given that BC and DF are congruent, so the chords, oops, I marked the wrong thing. If the chords are congruent, what conclusion can you make? Well, we're going to combine these two things. With all those theorems we learned, we could conclude that BC, the arc, is congruent to DF, the arc. If the chords are congruent, the arcs are congruent. And we could also conclude that the angle, the central angles are congruent. BOC and DPF are congruent angles. Okay, so use the circle to answer the following. Let's see. Let's do the what is the value of x one, and what is the length of RS. Okay, so looking at this diagram, what is the length of RS in circle O? So R to S is here. Well, since it's the same distance from the center, it's a distance of 9 from the center, and PR is also a distance of 9 from the center, then we know that PR must be congruent to SR because of the same distance from the center. And then they tell us that PQ is 12.5, and it's marked congruent to QR, so that must also be 12.5. So this whole segment here, chord, must be 25. 12.5 plus 12.5. And if PR is 25, and we know it's congruent to RS because it's equidistant from the center, then that means SR, or RS, has to equal 25 as well. Okay, and the last one, what is the value of x in the circle to the right? Well, notice 18 and 18, this whole segment is 36. And we are told that this chord is also 36. Well, if the chords are congruent, then the distance to the center must be the same. So x has to be 16. All right. Let's look at the next few theorems. Don't turn me off. You were going to turn me off, weren't you? You were going to fast forward me or something. Go get a snack and come back if you need to regroup. But these theorems are practically like one theorem. It looks like a lot, but it's really relating one thing here. This says in a circle, if a diameter is perpendicular to a chord, so if you know that you have a diameter, because it goes through the center, and it's meeting a chord at 90 degrees, all right, then it bisects the chord and its arc. Wow, that's a loaded situation. So if you know that it goes through the center of the diameter and it's cutting a chord perpendicularly, you know that it's perpendicular, then you could say this is congruent to this. It's bisecting it. CE is congruent to ED. Here to here is the same as here to here. And the arcs are congruent. Arc CA is congruent to arc DA. These should be arcs. Arc. Arc. Okay? So all because it's a diameter and it's going through a chord at a right angle. Next theorem is related to that. If the diameter bisects the chord, so it's just a different piece of given information. If you know that this is a diameter that cuts a chord in half, then you can conclude that this is a right angle. So up here we were given that it's a right angle, right? Perpendicular. Given that it's a right angle there, and we were concluding that these two things get bisected. Down here, we are told that it's bisected. So given that it bisects the chord, cuts it in half, right? Then it's a right angle. Okay, the last theorem here, this is the last one for the section, says that in a circle, the perpendicular bisector of a chord contains the center. In other words, take these two other theorems from up here and combine them. If you know that this is bisected at a right angle, okay, so you're given that it bisects at a right angle, 90 degrees, then it must be the diameter. That's going through it. This thing that's bisecting it at a right angle has to be going through the center. In other words, it's a diameter. Okay, quick summary of these theorems. Basically, when you have this situation that's drawn here, you know these are congruent if this is a right angle and it goes through the center. And the arcs are congruent too. Okay, so that is a quick diagram that kind of summarizes all three of those. All right, find the values of the missing variables in the following problems. We are going to apply all of these things here. If we are given a situation like part A, where you know that KL is a radius, you know that this segment KN is meeting this chord at a right angle, right? If it's a right angle, then we can conclude that this LM chord is getting bisected. Since it's a right angle and it goes through the center, then it's getting bisected. So therefore, if LM is 14 and we know it's bisected, this has to be 7 and that has to be 7. So we can do 3 squared plus 7 squared equals r squared to find the radius. 9 plus 49 equals r squared. 58 equals r squared. And r equals the square root of 58. If we want to put that as a decimal, we are just going to do, the square root of 58 is 7.6 approximately. And so that would be the radius, approximately 7.6. Part B, we're looking for y. We're looking for this segment here. I love this one. This one you got to really, really pay attention to. Let's put a star by it. Okay? Because this is the one that sometimes you're going to get to the point where you're going to be like, wait a minute, I have no idea how I'm supposed to do this. Whenever that happens, try to remember that every radius is congruent. Every radius is congruent within a circle. And you can draw any radius that you want from the center to the edge of the circle. So in this case, we are given y. We know it bisects AF because we're told it's 11 and 11. So this is bisecting. Our theorem said, well, if it's bisecting and it goes through the center, then it has to be a right angle. All right, then we've got a right angle. Then we have a right triangle. So if I take that right triangle and I redraw it here with, actually, let me redraw it this way. Right? I'm going to redraw this here. The right angle's here. This is y. This is 11. This is the hypotenuse. Well, we already have a missing side. We have to solve for y. So we can't have two missing sides. We have to know the length of that hypotenuse. Well, look at it. It goes from the center to the edge of the circle. So it has to be a radius. Do we know what the radius of this circle is? Yep. It's 15. Every radius is congruent within a circle. So if we know that the radius of this circle is 15, then we know the hypotenuse of this right triangle is 15. And we can solve Pythagorean theorem now. Okay, so you're going to be expected to know how to do that. Oops, 225. Okay, and we can solve from here. All right. I'm going to let you practice the rest of these. Let me give you some to actually make sure you do. Take a few minutes. Let's just do number 6. We're just going to do number 6, A and B. That's it for tomorrow, and we'll go over them then. Okay, thanks guys. Have a good day.